This course is how to inspect for moisture intrusion. And the goal of this course is to teach the student how to identify and report on moisture intrusion in homes and commercial buildings. So this is a very important course. And the course will teach you the best building practices and standards that make a home moisture resistant. Building practice and construction techniques are essential for inspector to understand. Building components that are defective, incorrectly installed, or simply missing can produce moisture-related problems. Moisture intrusion of a building can cause major structural damage and can threaten the safety of its occupants. Most E&O insurance claims in the inspection industry involve moisture intrusion. That's why we're doing this course. Once an inspector knows what property installed building components look like, they recognize the installation defects, and it becomes a lot easier to understand that and uh, see where it is. So, education and training on the best and most recent building practices for controlling moisture are essential for every property inspector. So, proper design and construction of homes involve moisture control to prevent deterioration. Recently, this has become more complex as expectations for managing interior moisture have risen. It now includes promoting occupants' comfort, protecting the indoor air quality, and preventing mold. Consumer demands better performance of their homes, making total moisture protection a challenging goal. Effective moisture control relies on scientific principles and practical implications by the builders. Property inspectors need to understand moisture control in relation to building standards and practice. This course combines common building standards with the property inspection practices. Now, understanding building methods and techniques is essential for inspectors. Defective or improperly installed components can really lead to that moisture related problems. So, moisture intrusion can cause structural damage and threaten occupants' safety. If water penetrates a building, it should be allowed to exit. Education on the best building practices is crucial for inspectors. Moisture related issues include rain penetration, structural decay, mold growth, high humidity, condensation, wet foundations, and of ice dams. These problems are mostly preventable and they are manageable. So the concept of moisture movement can be complicated to understand, and I get that. One issue is that we have and use so many terms, including like your air barriers, your vapor diffusion retarders, vapor permeable and impermeable. It's home inspectors often find it challenging and to speak, especially with other contractors and building officials, without using the same terminology. The most important term a home inspector should understand is a vapor retarder retards the movement of water by vapor diffusion. And vapor barrier is a vapor retardant of a certain class, well, class one vapor retarder. So many of these best practices will be found during a typical home inspection. And the lack of particular best practices for moisture management may not necessarily be a construction defect, potentially leading to the moisture intrusion. Caution during an inspection is advised when inspecting for construction practices because a typical home inspector is strictly non-invasive and it is just visible. Building components related to moisture management will usually be hidden, covered, or restricted in some way in a visual only building inspection. Now, moisture movement, to be able to inspect for moisture intrusion and related problems, being an inspector, you should understand the basics of how moisture can move through a house. Moisture and water vapor move in and out of a house in three different ways: with air currents, with diffusion through materials, and by the heat transfers. Of these three, air movements account for 98% of water vapor movement in a building cavities. Air naturally moves from high pressure areas to lower pressure ones by the easiest path possible, generally through any way, crack, hole in the building envelope. Now, moisture transfer by air currents is fast in the range of several hundred cubic feet of air per minute. Thus, to control air movement, a house should have intended air paths thoroughly and permittively sealed. So, the second law of thermodynamics, the moisture flow by vapor diffusion, is also governed by the second law of thermodynamics, where moisture will flow because of the condensation and the temperature gradient from high to low and from more to less. So it makes sense. And this means that moisture tends to move in colder climates from inside to outside. And in warm climates, it's from outside to inside. The laws of physical govern how moisture air reacts within various temperature conditions. The study of the properties of moist air is technically referred to as psychrometrics. A psychrometrics chart is used by professionals to determine at what temperature and moisture concentration water vapor begins to condensate. This is called the dew point. By learning how to determine the dew point, you will better understand how to diagnose moisture problems in a house. Now, the math. In addition to air movement, one can also control temperature and moisture content. Since insulation reduces heat transfer or the flow, it also moderates the effect of temperature across a building envelope cavity. In most U.S. climates, property, properly installed vapor diffusion retarders can be used to reduce the amount of moisture transfer, except deliberately ventilated spaces such as like attics and installation and vapor diffusion retarders work together to reduce the opportunity for condensation to form in a house ceilings, walls, and floors. Understand how water vapor moves can help home inspectors understand what they're observing when inspecting visible vapor diffusion retarders. So I'm going to give you a couple seconds to look at this slide and kind of understand how water vapor actually moves through uh, the water vapor, sorry, the vapor diffusion retarders. Okay, even without air leaks. Now, vapor diffusion and moisture control, small amounts of moisture in the form of water vapor can pass directly through the building's envelope through a process called diffusion. Vapor diffusion from damp or wet basements into the living space can significantly increase the moisture levels inside a home. Most materials and even glass are unable to completely stop vapor in diffusion. Thus, calling something a vapor barrier is a bit kind of on that wrong side. So, the current trend in building science is to refer to materials as vapor retarders, which means that while they're retard or slow down that movement of water vapor, they do not completely halt that process. Materials and significantly slow down the vapor diffusion process are said to have low permeability or simply low perm. Typically, building codes consider a material to be vapor retardant if it has a perm rating of 1 or less. Now, those retarders are often applied in crawl spaces of the building to prevent ground moisture from evaporating and traveling up into the home. Many building codes require such vapor retarding materials under wall boards to prevent vapor diffusion from bringing water into the structural assembly. In cold climates during the heating season, pressure differential drives the vapor from the inside of the building to the outside. Now, places like Minnesota, where I'm from, the vapor barrier is generally installed on the interior face of the wall studs. The warm climates during the cooling season, the vapor drive is from the outside of the building towards the inside. Thus, like in Miami, Florida, vapor retarders are often applied on the outside of the building bes beside the perm rating of the material. The effectiveness of a vapor retarder is also the function of its surface area. Vapor diffusion retarders that cover about 80% of the building is said to be 80% effective. So it makes complete sense. In most North American climates, vapor barriers, or even actually vapor diffuser retarders, should be part of that moisture control strategy for a home. A vapor diffusion retarder is a material that reduces the rate at which water vapor can move through a material. The older term vapor barrier is still used even though vapor diffusion retarder is more accurate. It is a myth that installing a vapor diffuser retarder is most important step for controlling moisture in the walls. Vapor retarders only retard moisture due to diffusion, while most moisture enters walls through the via fluid capillary action or through air leaks. Sorry. Water vapor can also be carried through the building components by diffusion, driven by pressure and temperature differences. Vapor diffusions can be impeded by use of vapor diffusion retarders. And vapor diffusion retarders can help control moisture in like your basements, your ceilings, crawl spaces, floors, the slab on grade foundation, and walls, of course. Effective moisture control in these areas are throughout the home must include air sealing those gaps in the structure, not just the use of the vapor diffusion retarder. How, where, and whether a vapor diffusion retarder is needed, depending on the climate and the construction of the home. So in 2015, the International Residential Code, or the IRC, defines vapor retarders based on their permeability. This ability of the material to retard the diffusion of water vapor is measured in the units known as perms, or permeability. The highest or the higher the perm rating, the more easily water vapor can pass through it. So in 2015, the IRC describes three classes of vapor retarders, including the class 1, 2, and 3, which are directly related to the perm rating. And so you can actually see on that slide there, 1, 2, and 3 of the classifications there. Okay. The NWA crawl spaces, climate zones for class 1 and class 2, uh, climate zones 4A, mixed humid, does not require vapor retarders, but if not installed, will require vents within 3 feet of the house corners and one for every 150 square feet. Class 1 vapor retarders, that's 1 perm or less, including glass, sheet metal, unperforated aluminum foil, polyurethane sheets, and rubber membrane. Some builders refer to Class 1 vapor retarders as vapor barriers, but the code no longer uses that term, so remember that. Vapor barrier is not really accepted anymore. Class 2 vapor retarder, that's the greater than 1 perm and less or equal to 1 perm, including unfaced expanded or extruded polyurethane, 30-pound asphalt coated paper, and plywood bitumen coated craft. So, and it's always a good idea to actually take a screenshot of this too. It's kind of nice to actually teach your customers about this too. So because of the change in the 2009 RRC, Class 3 vapor retarders, latex paint, are known permitted in several climate zones. See the table 2 below here? When the wall is constructed in a way that allows drying through the use of vented cladding, that's brick or lap siding, and airspace that allows that airspace behind it, or reduces the potential for condensation by the use of insulated rigid foam sheathing. So the U.S. Department of Energy, or Building American Sciences, cautioned that the recommendation to install a vapor barrier on the warm in winter side of the wall assemblies is difficult to apply in mixed climates or climates that are air conditioned in the summer. They recommend that walls should be allowed to dry to the inside, the outside, or both sides, and they don't recommend the use of class 1 vapor retarders in any but the coldest of clients. And you can find out more if you go to www.energy.gov/EERE/buildings um, hyphen America. So you can find a lot more of information out there. So vapor diffusion retarders are typically available as membranes or coatings. Membranes are generally thin, flexible materials, but also include thicker sheets, materials sometimes called structural vapor diffusion retarders. Materials such as rigid foam, insulation, uh, reinforced plastics, aluminum, and stainless steel are relatively resistant to water vapor diffusion. These types of vapor diffusion retarders are usually mechanically fastened and sealed at the joints. In mild climates, such materials as painted gypsum wallboard or and plaster wall coatings may be enough to impede that moisture diffusion. In more extreme climates, higher perm vapor diffusion retarders are advisable for that new construction. They perform best when installed closest to the warmer side of the structural assembly, towards the interior of the building in cold climates and towards the exterior in hot and wet climates. The vapor diffusion retarder installation should be continuous as close to perfect as possible. This is especially important in very cold climates and in hot, humid climates. Care should be taken to completely seal any tears, openings, and punctures that may occur during construction, except for extensive remodeling projects. It is difficult to add materials such as sheet plastic and vapor diffusion retarders to an existing home. Obtaining an energy audit and thoroughly sealing any leaks it reveals a very effective strategy for slowing down that moisture movement in and out of the home. A home may not need a more effective vapor diffusion retarder than the numerous levels of paint on the walls and the ceiling unless it's located in an extreme northern climate. The vapor barrier paints can be an effective option for existing homes in colder climates. The perm rating of the paint should be indicated on the label. For instance, glossy paints are generally more effective vapor barrier or diffusion retarders than the flat paints are. And the acrylic paints are generally better than the latex paints. So all appropriate surfaces should be covered, or moist air within that cavity may condense, which could lead to dampened insulation. The thermal resistance of damp or wet insulation is dramatically decreased. The prolonged wet conditions will encourage mold growth and wood rot. So we don't want that. An air barrier vapor diffusion retarder attempts to accomplish water vapor diffusion and air movement control with one material. This type of material is most appropriate for southern climates, where keeping humidity outdoor air from entering the building cavity is crucial during the cooling season. In many cases, air barrier or vapor diffusions retarders consist of one or more of the following materials: polyurethane plastic sheets, the building foil, the foam board insulation, and other exterior sheathings. So moisture is common cause of building degradation. In fact, much of what we know about applies building science today originates from early work investigation on moisture impacts on buildings. While the severity of moisture problems vary greatly depending on the climate, few regions in North America are free from concerns about moisture in buildings. So, moisture can attack a building durability on many fronts, from wet crawl spaces to the leaking roofs to the moisture-rich air, and can even become trapped in the building structure assembly, possibly leading to the mold growth that we talked about, the rot, or insect infestation. Entire industries have developed that specialized in way of combating these various moisture problems. So, part two, inspecting for moisture intrusion. The following section refers to the building practices that prevent moisture problems, which may be consistent with minimum building codes and the standards. There are practical practices that go way beyond the code requirements. Home inspectors are typically not required to um, stand, inspect for the code compliance. However, knowledge and the understanding of building codes and standards are sometimes necessary in order to inspect the building practices that are causing moisture related problems, such as missing kickout flashing, that should be installed according to the US building standard. Commenting upon the codes and standards beyond that scope of a typical home inspector or home inspection. But home inspections are not code inspectors, but home inspectors do use building codes and standards as reference sources. Keep that in mind. So, roof coverings provide the first line of defense against the elements. They also tend to be the most exposed component of a building exterior envelope. Therefore, roof coverings should be selected, detailed, and installed to provide durable resistance and uh, to water penetration. So, because more than 75% of all homes in the US use composition roof shingles, we will focus on this type of roof covering in this section of the course. Home inspectors should know the importance of the minimum roof slopes for the various roof coverings. Underlayment installations are not readily visible, except for possibly at the eaves and the rake by gently lifting up the edges of the shingle. Now, just a warning here, if you're going to be doing that, be sure not to tear or damage those shingles. So, understanding minimum roof slope and check the underlayment. Steep slope roof systems are defined as the National Roofing Contractors Association, the NRCA, as systems designed for installation on slopes greater than 312 or 14 degrees. Steep slope roofs are water shedding, but they're not waterproof. Let me repeat that. Steep slope roofs are water shedding, but not waterproof. Therefore, the roof slope is limited in accordance with Table 1 above for various steep slope roofing products. To prevent water leaks, these roof systems rely on fast drainage, adequate overlapping of elements, and the use of underlayment as a backup layer for protection. For composite uh, Gotta take a breath here, sorry. For composition shingles and concrete and clay tiles, figure one below shows a double underlayment detail to be used on slopes less than 412 for those two types of roof coverings, just FYI. For roof slopes between 212 or 2 units vertical and 12 units horizontal equals 9.5 degrees slope. To a 412 vertical and 12 units horizontal 18.5 degree slope, underlayment should be 2 layers applied in the following manner. A 19-inch strip of underlayment felt should be applied parallel to and starting at the eaves and fastened significantly to hold in place. Starting at the eaves, 36 inches wide sheet of underlayment should be applied overlapping successive sheets at 19 inches. So you're looking at them like this, and fastened significantly to hold in place. For roof slopes of 412 and greater, 1 layer of underlayment should be applied to in shingle-like fashion. It should start from the eaves and run parallel in the eaves. It should overlap 2 inches. It should be fastened significantly to hold in place or sufficiently. Um, End laps of the underlayment should be offset at least 6 feet. In areas where there is a history of ice dammings forming along the eaves, causing a backup of water, an ice barrier that consists of at least 2 layers of underlayment cemented together or of self-adhering poly modified bitumen sheet shall be used in lieu of normal underlayment. They extend from the lowest edges of the roof surfaces to the point at least 24 inches inside the interior wall line of the building. Detached structures without conditioned areas are the exception. By contrast, the low slope systems are designed as waterproof roof systems and use a covering design for slopes as low as 1/412, 1/412. While low slope roofs are commonly known as flat roofs, an actual flat roof surface is a design mistake, and you really should call that out. Um, there should always be some sort of slope there. Optimizing slope of a water shedding roof consists considering several factors. A moderate roof slope of 412 to 712 provides a favorable balance of pros and cons for water shedding systems. For example, the low slope roofs will tend to decrease drainage efficiently, allowing debris to accumulate and increase wind uplift loads on the roof. In addition, as the roof ages or becomes damaged, leaks are very likely to be more severe. While very steep roofs will tend to decrease drainage efficiently, they increase the building and roof's exposure to lateral wind loads. Furthermore, water flow velocity will be increased, and partly at the valleys, which may cause some sour. So, in most homes are designed for a maximum roof covering weight of no more than 5 per square foot or PSF. When replacing the roof on an existing homes, a structural analysis should be performed if a light roof covering is being replaced by a much heavier roof covering. During a typical home inspection on an existing roof, this type of identification will not be possible. However, on a new home being built or on a roof installation project, the rating identification could be accomplished. So, fastening. There is a good and bad fastening. The manufacturer's installation instructions should be followed, and the fastener should be properly installed. Appropriate fastening spacing, fasteners installed without damaging material, etc. In in general, in general, 6 roofing nails per shingle, rather than the standard 4, are required for composition shingles in high wind regions. The the roofing fastener should not be overdriven. I've seen that done hundreds of times so that the head damages or tears actually the shingle to avoid complete loss of the shingle strip, which is a major cause of excessive water damage to the contents of the home during wind-driven rain events. So attention to the fastening quality is equally important for other roofing materials such as tile and metal. So the underlayment, typically 15 tarred felt or underlayment, provides backup protection against water intrusion only as long as the primary roofing material remains intact. It is not intended for direct exposure in the event of loss of the primary roofing system in a severe wind-driven rain event. To enhance protection against water intrusion and damage to the building and the continents in severe wind-driven rain climates, a roofing contractor should apply a continuous strip of bitumen adhesive tape to sheathing joints prior to installing the underlayment. This practice provides a level of protection against water intrusion, even in the event of severe wind damage to the primary roofing. For further backup protection, a self-adhering bitumen material membrane may be applied to the entire roof. So check the roof sheathing. The roof covering is only as strong as the substrate to which it is attached. Roof sheathing Roof sheathing in high wind areas should be attached with a minimum 8D nail. That's a 0.113 inch diameter. Deforming shank nails or 8D common nails, and that's a 0.131 inch diameter, just FYI, spaced 6 inches on the corner at the framing members. Full round head or D head nails should be specified and should not be overdriven into or through that sheathing, as this really weakens that connection. So don't want to see that. Roofing and re-roofing for hail damage protection. Composition shingles tested in accordance with the UL 2218 and rated as class 4 may be used for improved hail resistance. Class ranges from the low of 1 to the high of 4. In some states, such as Texas, hail damage insurance premiums may be reduced with the use of impact-resistant roofing. In fact, in October of 2004, the Texas Department of Insurance provided an online listing of manufacturers of products that meet the state's roofing discount requirements. And you can find that out at www.helpinsure.com/home/roofingx.html. Another consideration for projecting roofs from protecting the roofs from the hail damage involves re-roofing. Now, re-roofing over an existing layer of composition shingles, while generally permitted by code, reduces the ability of newer shingles to resist impact damage from hail. Therefore, in hail-prone regions, the insurance industry recommends, and the local code may require, that re-roofing should include removal of the existing layer of the old shingle roofing, just FYI. Minimal roof penetrations increase the likelihood of water leaks due to failed gaskets, sealants, and flashing. The number of roof penetration may be reduced by a variety of technologies and strategies, including air admittance valves, which we used to call them cheater valves, to reduce or eliminate plumbing vent stack penetrations. Consolidation of vent stacks below the roof, and exhaust fans cap routed through the wall instead of the roof. High efficiency combustible combusted appliance, which can be sidewall vented, and electrically powered HVAC equipment, water heaters that do not require the flue. So the more penetration an inspector finds passing through that roof covering, the greater chances of in intrusion. So we want to make sure that that's uh, checked. What else? So the roofing flashing. While penetration is commonly associated with flashing and detailing problems around roof penetration, eaves, and wall intersections with a low roof section, the following best practices describes flashing details for common applications in residential construction that inspectors should be able to recognize. These conceptual details are intended to help the inspector understand the objective for roof flashing, as found in the 2006 IRC, International Residential Code. Okay, this figure provides models for correct flashing installation techniques for asphalt composition shingles roofing, which is the most common roofing material used in residential construction in the US. For flashing details for other roofing styles, the inspector should refer to the manufacturer's guidelines for that industry. Keep that in mind. Table 2. This is pretty awesome. The roof flashing. Give you a few seconds to look at this over because this offers normal the normal width requirements for the ice dam flashing at the eaves based on different roof slopes and the eaves overhang. Note that for many scenarios, a single 36-inch roll of flashing may not be sufficient. The roof system ventilation and installation are important for a number of reasons. Condensation control, temperature control, energy efficiency, and the prevention of chronic ice dam formation. Ventilation of attic areas intended to prevent the accumulation of moisture vapor in the attic or the roof space and to dry low levels of condensation that may form on the underside of the roof deck. Ventilation is also intended to reduce the temperature of the roof deck during hot weather to improve shingle durability. Reducing the attic's temperature through ventilation and insulation also provides energy efficiency during hot periods, and in the case of ice dams, elevating attic and roof temperatures during the winter can cause snow on the roof to melt. Insulation and roof ventilations help to keep the roof exterior surface cold, and that helps minimize the development and melting water and consistently with those ice dams. Ventilating those roofs in extreme hot or humid conditions may add, rather remove moisture from the attics and enclosed roof spaces. So, however, not ventilating roofs may void the asphalt composition roofing manufacturer's warranty and slightly decrease the life expectancy of the roof material due to increased temperature of the roof surfaces. Now, other tiles, concrete on roofing materials would not be similarly effective, just FYI. Employing an unvented airspace may require designing the attic roof space as conditioned space. Similar to the requirement that creating habitable spaces in the attic. There are several sources which with more information on unvented attic design, traditional attic ventilation remains a cost-effective through imperfect solutions for moisture control. In colder climates, roof ventilation serves to remove the humidity and condensation from the roof attic space and helps to prevent the chronic formation of those ice dams in those areas at the eaves. So, what causes ice dams? Now, I don't see those too much in Florida, but I definitely used to see them up in Minnesota all the time. An ice dam is caused by warming of the attic space. And while attic ventilation and insulation contribute to the prevention of these ice dams by keeping attics cold, they can be overpowered by the attic's warming effect, such as air leakage from the house into the attic through the ceiling bypass, the chassis, the open gaps, or uninsulated areas or ducts. And if significant conditions, air escapes into the attic through the bypass, the attic ventilation will not be capable of preventing the warming of the roof decking and subsequent those ice dams. Therefore, sealing air leaks between the house and the vented attic is essential to make the attic uh, seem cooler. Therefore, you have to seal those up. It is essential on making that attic ventilation really work in that whole area of your house, because that attic is very important. Check out the section 2.55 there for information on inspecting methods, practicing of preventing air leakage into attics. Air leakage from the interior into the attic also intru- introduces that moisture factor. If significant interior air leaks into the attic, attic ventilations may not be. Sorry about that. I was trying to hold that sneeze. It didn't work. If significant interior air leaks into the attic, air ventilations may not be significant to prevent attic moisture and condensation problems. For enhanced protection against these for formation of ice dams, this table 4 provides recommendations, level of insulation and ventilation ratios as a function of the venting layout. These recommendations should be found in the area with the ground snow load greater than 30 pounds per square foot and in other areas where ice dams are a concern. The recommendations for ventilation in Table 4 can additionally be used by contractors to create multiple lines of defense for the flashing to prevent these ice dams. And that is very important. Also, the arrangement of the vent areas must balance high or outlet the low or inlet vent openings. I know that was a lot of information there, but we'll keep going. Roof overhangs and projections such as porch roofs, overhanging upper floors provide a primarily means to deflect rainwater away from the building walls. Thus, the potential for water prevention through siding, windows, and doors is minimized. Because the protection of roof overhangs increase with the increasing overhang width, larger overhangs than those recommended in the selection may be important in consideration of weather resistant wall barrier design. Roof overhangs often offer limited benefits during periods of severe wind-driven rain conditions, such as thunderstorm fronts and tropical storms. And in arid regions where rain is not as major concern, in severe wind-driven rain climates, a good performing weather-resistant barrier for walls is at least as important as providing roof overhangs. Refer to that section 2.3.1. In high wind areas, overhangs add wind uplift load to the roof and may require stronger roof to wall connections. So While the roof overhangs, the porch roofs, while the roof overhangs and porch roofs protect the building walls from impinging rains, gutters serve to protect building walls and foundations from roof water runoff. Roof gutters, downspouts, and leaders or diverters from the initial component of a drainage system for the building and site. So I'm going to clarify that just a little bit here. So when you have the gutters, that serves as the protection for your walls and your foundation. So you want to make sure that the downspouts are shedding that water away from the property. Common problems with these guttering guttering are associated with installation and the maintenance. Home inspectors can check if its properly sized materials are being used. If the guttering is appropriately sloped towards adequate size downspouts, and if the discharge is directly away from the building foundation and the perimeter. Discharging the water at the inside building corners should be avoided. Some local storm water codes may require special infiltration or filtration treatments of the roof runoff, just FYI. In certain areas, that is actually very common. The the rainfall intensity for roof drainage designs is sometimes based on a 10-year return period and 50-minute duration. Now, however, other design return periods and durations may be used effectively. Adjustment factors for other acceptable designs conditions are given below. A standardized design creation in US building codes does not exist. So practical experience and judgments are very important. So check that roof drainage system at all. I think it's one of the most important systems that should be on every house. Based on selective guttering sizes and the types, as well as the design rainfall intensity from step one, the maximum plan, the horizontal area of the roof and the gutter can adequately serve can be determined by using the table here. Based on the area and the roof's geometry, spacing and locations of downspouts can be determined as shown in the example below. If using special sizes for downspouts, the gutter size will generally control the spacing of the downspouts. Downspouts with a dimension of less than 2 inches should be avoided. Makes sense, right? It is also generally recommended that downspouts should serve no more than 50 feet of gutter length. A commonly used gutter is the 5-inch K-style gutter with a 2 by 3-inch rectangular downspout. Now, roof rainwater collected in gutters and delivered to a grade VI downspouts must then be moved away from the foundation onto the property graded soil using leaders and diverters. This third component is just as important as the first two and should receive equal emphasis. Now, leaders should direct the downspout discharge of a minimum of 2 feet away from the building perimeter. This can be done using splash blocks or an underground drainage pipe such as corrugated polyurethane or smooth PVC piping, which discharge to safely to discharge that away. In particularly poor soil conditions such as expansive clays or collapsible soils, which has been severely weakened with that increased moisture, the distance um, between the downspout discharge and the foundation should be increased. Now the code R703 exterior covering. This is a fun one. What is a weather resistant exterior wall envelope? Okay, other words known as the WRE. This section discusses what a home inspector should look for with water resistance wall envelopes, which can include siding, water barriers, etc. Current U.S. building codes don't distinguish between the inherent performing differences of the various weather resistant envelope, the WRE systems. In addition, sections of the siding systems generally focus on that added attributes. Sorry, I got to read that section again. I am so sorry. I got all these notes here and I just lost my place. So let's start over. In addition, sections of the siding system generally focuses on attributes to such as appearance, cost, and durability. There are different types of cladding systems that protect a building from the rainwater penetration and the accumulation of in the walls. This section is intended to show the home inspector the basic installations of the water-resistant wall envelope as described in the 2006 International Residential Code, R703.1 General. So, exterior walls shall provide the building envelope or building with the weather-resistant exterior wall envelope. The exterior wall envelope shall include flashing as described in section R703.8. The exterior wall envelope shall be designed and constructed in such a manner as to prevent the accumulation of water within the wall assembly by providing a water-resistant barrier behind the exterior veneer, as required by section R703.2, and a means of drainage water that enters the assembly to the exterior. Protection against condensation in the exterior wall assembly shall be provided. There are some exceptions. I love reading code. Due to the potential of water accumulation within the wall cavity, a water-resistant membrane must be installed behind any exterior siding and vinyl and veneer. Sorry. Under certain condition, it is permissible to eliminate the membrane in detached accessory buildings or where the siding, finished material, or the lathe provides the needed protection. The following 2006 IRC language defines a water-resistant barrier. Let's get into some more code. Isn't that fun? R703.2 water-resistant barrier, one layer of number 15 asphalt felt or other approved water-resistant barrier shall be applied over the studs or sheathing of all exterior walls. Such felt or material shall be applied horizontal, with the upper layer lapped over the lower layer not less than 2 inches. Where joints occur, the felt shall be overlapped at least 6 inches. So the installation of even the most weather-resistant wall envelope system on a house does not diminish the need for proper installation, particularly with the regards to a flashing detail as penetration. In addition, the use of the roof overhangs provide performance benefits for all cladding systems by reducing the moisture load experienced over the time and by allowing greater opportunities for wall to dry in the event of the periodic wetting due to wind-driven rain. The life expectancy of various siding materials may vary widely from 10 to as long as 100 years or more, depending on the type of material, climate exposure, maintenance, and those other factors. Understanding a weather-resistant envelope system. Now, a drainage cavity, the WRE system, will provide fair to good protection in nearly all the climates and building exposures, and should be considered as a common and broadly applied wall design for moisture protection. In most severe cases, such as climate Climates with that severe wind-driven rain or openly exposed buildings with no overhangs, and for wall designs involving different types of material, such as like conventional your stucco and things like that. Alternative WRE systems may be installed based on the climate and the building exposure. A three-step design process that accounts for these factors follow in this section. So you got a rain screen, and a rain screen can be considered an incremental improvement over the drained cavity approach. This type of WRE is uncommon in the US, but has been used in Canada to address severe climate conditions by the addition of some details to help reduce the air pressure differential across the cladding systems during the wind-driven rains events. So water penetration into those drainage cavities is further limited. At a minimum, this approach involves use of an air barrier behind the cladding to resist the wind pressure. Thus, wind pressure across the siding, which is vented and not airtight, is reduced and is less likely to result in water being driven through the siding due to pressure differential across the siding. So also the cavity between the cladding and the air barrier must be compartmentalized by the use of airtight blocking or furring at the corners of the building as a minimum practice. This feature prevents pressure differentials on differential surfaces of the building from communicating through a continuous cavity behind the cladding, which can cause unintended pressure differences across the cladding and drive rainwater through the cladding into the drainage cavity. Because many of these requirements components of a basic rain screen system are already present in simple drainage cavity wall systems. Drainage cavity systems are generally considered a more practical alternative for these typical applications. So we're talking about the moisture resistant wall systems. These type of systems are really essential when it comes to protecting your home. A lot of times, like I will be watching uh what is that show? The Homestead Rescue. And I can see that there's so many different avenues that they should be taking and they don't take it. And it's like, oh, maybe I should just join that show. So the climate conditions are based basics of the potential for wetting of those walls, especially wetting from wind-driven rain. We're going to talk about that quite a bit. The exposure categories can be referred to as severe. That is, severe conditions that can result in frequent wetting due to the wind-driven rain, such as coastal climates and areas prone to frequent thunderstorm areas. I, my family and I took a trip over to uh, St. Augustine, and we saw like a lot of those houses that got uh, damaged from a lot of wood driven rain. And I even told them, hey, if you want me to do a home inspection, maybe we can work out something here and teach them. So, moderate climate is conditions pertain to those sites that are particularly exposed to the wind driven rains and have that low climate condition in association with relatively dry climates with little rain or wind-driven rain. So this map here actually shows you the clarity of where the wind-driven rain really is, and it's normally like right on that east coast there, and it kind of goes up a little bit into the Midwest, but and a little bit out by California there. So the above classifications are initially subjective as there are no clearly defined criteria in the US for assisting with that wind-driven rain, and its effect on the building wall system is really hard to uh, get a real grasp on it. And I totally get that because I've been a home inspector since 2018 and I've seen a lot of stuff. And I think it's really important that we continue with the understanding where that moisture kind of goes into the building and where it excesses in that building exposure, the terrain surrounding a building impacts exposure to that wind-driven rain. And so it can have a big effect on the building envelope, the building system. And so the ratio of the roof overhang, so if you have that overhang with to the height of the protected wall below, so if you're looking at the protection of that overhang, it actually protects that wall below using alters and exposure of the building to the weather and wind-driven rain. So, uh, like I said, I grew up in Minnesota, and so whenever there was snow, and you probably have this in New York and a lot of these colder places, and right where that overhang is, you can see that the snow would accumulate right outside that area, and you could actually walk around the house without getting your shoes wet. And a lot of times that's that building overhang. And if you think about that rain that impacts that, the same thing happens there. And so this table here may be used to determine a building's exposure level based on the climate condition, the roof overhang ratio, and the wind exposure. it, the exposure level then leads to reasonable weather resistant envelope approach. So does that make sense? I trying to get this so that it's a little bit more involved because there's so much that can happen when you have a lot of wind driven rain, and it can expose that area of the house to the point where you can have that moisture coming in. And understanding how the building is set up, uh, it exposes this manner can really guide you as an inspector and the importance of the flashing detail and potentially benefits of having a greater overhang installed. So that's why it's really important to actually look at the building outside and inside. So based on the weather resistant envelope, based on that building exposure level determined in that step two, the WRE approach may be selected and installed based on expectations of relative performance. So kind of think about that when I'm talking about that overhang, that snow that's coming in there, that you got that little bit of a gap there. Alternatively, other factors may be reconsidered in the building and the site design to improve protection from that rain, such as use of larger overhang. So if you had a larger overhang, the less snow that's actually going to get in there. So think of that as like the rain, because basically that's all snow is. It's just frozen rain, right? So if the exterior water repellent coating to the masonry is apparent, pay close attention to the fact or the face of the product to make sure that the spalling is not occurring. Often the wrong product has been applied and is not permeable, causing that water to be trapped inside, and that face of masonry will spall due to capillary action, causing hydrostatic pressure. And I think you probably remember, like, I'll see that a lot on chimneys and stuff, where that the the brick is actually falling off because there has been uh, rain that's gotten in the brick itself and actually caused it to freeze, and then it expanded, and that's what that hydrostatic pressure, the thermal expansion, and can cause problems with that moisture. So I always think of that when I'm looking at roofs and seeing that chimney coming up and looking at that, because it's really it's simple, but it's very hard to find when you're in a hurry. So take your time when you're doing these type of inspections. And I've done a lot of zip board inspections too on new builds. So I've understood how cavities and stuff like that work. And I also work with Habitat for Humanity. So I've installed walls and installing windows and doors and understanding and helping them understand the moisture that we can prevent to help uh, that homeowner. So the three major areas are like your windows and your door frames. Typically, uh, in conventional residential constructions are wood, right? So vinyl and aluminum are somewhat used, but windows and doors can be key contributors to the water penetration in walls from either the flashing failures around these components or the characteristics of the components themselves. So this section discusses the feature of window and door components that may reduce leakage and related moisture problems. So without careful installation of the window and door components, it should be assumed that they will leak some amount of water into the wall cavity. Uh, Simply relying on the window and door products that are labeled according to the standard test methods does not necessarily guarantee that the water leakage will not occur through those frames and in the walls. Frames that rely on sealants and seals, typically like at the joints, will eventually leak water as these joints fail over time. The life expectancy of a window and door units may vary radically. So you can have window that'll last for 10 years. You can have a window that lasts for 50 years plus. I think we lived in a house that had 70 plus year old windows, and there was quite a bit of leakage there, but the windows were actually in really good shape. Depending on the unit type and materials, exposure, the maintenance, the types of seals, and the sealants used at the joints, and all those other factors all rel play a part. So the frames that rely on the welding joints, so right where they meet, where you got your window and that come up and it's kind of like this sometimes and sometimes it's like that, whatever, will generally provide a much longer moisture resistant service life. So when we put in it's funny because I'm looking at this picture and seeing how we put in windows, and we'll always put them in there and we'll frame them up. We'll make sure they're level, and then we'll put the uh, the sealant around the outside of it after we actually put sealing on the inside. So we're inside, put the sealing around the flange. We shove the window into the proper place. Then we actually put the joint compound around there, or the tie back tape is what we call it. And so that's what we always use. Many of these have they have weep holes that allow that water to discharge if it does get behind there. So, and that should be free from debris, and so always check that out if they have it. Some windows don't even have them anymore. Well, they have them, but they don't have them visually. They actually go behind the siding. I've seen those done, and I'm not a big fan of it, but that's okay. In the absence of relevant installation details for specific applications and combination of exterior envelope, the manufacturer should be consulted. In addition, industry standards, installation guidelines may be consulted, such as ASTM E2112-01. That's a big word. But a lot of times, like I've done so many inspection with that zip board, and a lot of those manufacturers don't put them on right because they're supposed to do it a certain way, and I can't um, emphasis enough on the right building um, guidelines that they should be following. So the high performance windows have a system for weeping intrusion water that acts much like the rain screen that we talked about, the wall system as previously discussed. It In severe wind-driven rain conditions, in high exposed conditions such as high performance windows and door systems should be preferred for the same reason. That cavity and the rain screen, the WRE systems are preferred. So the recommendations above the detailing window and door frames can generally be checked by inspecting the manufacturer's technical specifications showing a cross-section of units, including the dimensions, the seals, the thermal breaks, and other factors that may create leakage paths, such as corner frame joints and mold joints in the multiple window assembly. Now, like I was saying with that zip board, I was inspecting this house, brand new build, and they weren't putting it on right, and they have to do it a certain way. So I actually called the manufacturer of zip and talked to the rep about how to actually install this properly, because the most important thing is my customer getting the right value that they deserve. And so they actually went out, and now this building, I'm not going to say who the builder was, but they actually stopped using Zipboard because they didn't want to follow the recommendations. And I had a part to play in that. And there's so many houses out there that are going to have problem because they didn't understand how to flash that window properly and use the stretch tape and the zip board properly. So it's very important that you understand how things are built. So if you don't build houses, I recommend volunteer at Habitat for Humanity and try to get some exposure to it so that you understand how things are built. So water penetration and accumulations in walls are most commonly assorted with that flashing and detailing problems around those windows and doors and other penetrations through the water resistant wall envelope. So we got to really pay attention to how things are put together. In this figure here, some typically yet very important flashing details are provided as general models for correct installation techniques. These are not present as the only solution to flashing. So there's many ways of doing it because there are certain variables that can happen in this. And we want to make sure that when you're thinking about rain, remember water always flows down. But when you got that wind-driven rain, it can get into those corners and stuff. That's why, like, if you had a RV or something, you shouldn't really pressure wash it because you have so many envelopes inside the RV that the water can actually penetrate that if you use a pressure washer. So kind of good information to have. So the flashing is another defense against getting that water out. So if you're looking at this here, now think of the brick, you got that little bit of space in between there because we want to have water will permeate that brick, but we have to have a way for it to get out. And they figured this out, I believe, in the 1800s that a lot of these walls were starting to bow out, and I've done a lot of those houses in Minnesota where there was a big bulge in the brick because water got behind there, it froze, and it pulled apart. And you've seen that. I know if you've done stucco houses, you've seen that too. So we want to make sure that that water has a way of getting out. So check those weep holes, check those cords, make sure that they're there, and check that flashing. It's very important. In the construction of the weather resistant envelope, the WRE again, system, there will be joints and seams that require or at least benefit from the appropriate use and maintenance of caulking and seals. In the absence of guidelines for specification and applications of the caulk and sealants in model building codes, this section provides valuable information for us as inspectors regarding their use. And caulking can save a house, and it is required by the manufacturer installation instructions. And specified caulk material should be followed carefully by the installer and then checked by the inspector. So when I do my phase inspections, that's one thing that I'm checking a lot, and I always say caulk because that's how it should be pronounced. In general, caulks and sealants should not be relied on as the primary defense against the water intrusion at the joints in the WRE system. Flashing is preferred whenever feasible. Even when caulk is additionally used, the standard quality caulking and the application practices combined with the shrinkage and the swelling of the building components usually result in the onset of granular failure of the watertight seal within a few years. So that caulking does actually expand and contract. When they came up with the LP system on houses, they would butt both the LP up and they would leave a 1/4 inch gap and then they would actually caulk in between that. Well, what they found out that when it expanded, it would pull that caulking seal off and then there was a seam there. Water could get behind there. So now what they do is they actually put another Tyvek or water barrier or behind there, and then they put that on there. Then that's how it's sealed. So the caulking isn't relied on 100% anymore. So caulking can prevent that water damage inside the and outside of the home when applied around the faucets, ceiling fixtures, water pipes, drains, the bathtubs, and all those plumbing features. Caulking also can be used as a seal to seal those air leakage too. So some general information regarding the types of caulking and sealants provided here in Table 9 include longevity, the best uses, and appropriate types of joints for given sealants. With proper adhesive adherence of the manufacturer instructions, typically with the respect to surface penetrations or preparation, high quality caulks and sealants can be made to endure for reasonable length of time between maintenance and replacement. Normally about 5 years is considerably long when it's not severely exposed. So silicone, rubber, and urethane caulks generally give the best overall performance for applications to exterior building envelopes. For bath and shower applications, mildew-resistant silicone caulking are also available. I actually did a blog on this about 2 years ago. High quality caulking installation requires appropriate ambient temperature, so dry, clean surfaces, and the adequate joint gap to allow the caulk to elastically pull and without pulling loose from the caulking part. So when you're caulking two joints together or whatever, you want to make sure that bead is running in there. And when you got that thermal expansion, that it doesn't break that seal. So you want to put enough in there so it actually stretches with it and pushes out. And like I said before, with that LP siding, when it pushed together because of the heat, um, it would actually squeeze that caulking and you'd see all these like little bumps all over the whole side. It didn't look the best, but it worked. Inspection of caulking is strongly recommended, especially around those windows and doors. Matter of fact, I think it's one of my biggest call outs is caulk these windows. Many sites are considered normal and fall within the standard condition addressing in the residential building code. However, the use of marginal sites, which is becoming more common without the proper site design, can result in costly mistakes such as foundation, structural, and moisture problems. Appropriate foundation envelope, sorry, the elevation and drainage pattern for these sites should be considered. So when you're looking at that house, make sure that you're checking the drainage pattern because, if you're not controlling the water will control you. So check that site drainage. When a house is being built, a site plan should be developed to do more than just locate the building and the utilities and demonstrate compliance with the setbacks and the zoning requirements. The site plan should also account for the drainage plan that indicates the slope of the land and the drainage pattern for that building site. For sites that generally provide natural drainage away from the building location, the main concerns is established as appropriate foundation elevation to maintain drainage. And that's the whole thing is we want to get that moisture away from that building envelope. It's definitely important for that. And I've always said if you can't control the water, that water will control you. So model building standards typically require a minimum of 6 inches of fall in a ground level. So over a distance of like 10 feet, 10 feet, from the perimeter of the building, provide that additional slope is good method to offset the future settlement of the foundation backfill next to that building, unless the soil is moderately compacted or tapped during that backfill process. So poor site drainage of the surface water is perhaps the most important contributor to foundation moisture problems. Wetness of the site, soil bearing conditions, and the slope of the site are key factors in making a decision on whether to build and how to build a house. When poor site conditions exist, they can often be overcome technically, providing that there is land use restrictions. There is no restrictions there. When poor site conditions exist, they can often overcome this technically. So any anything is possible whenever you're building a house and you see something that isn't quite right. You can actually see that there is a solution for every problem. It's depending on where that how bad that system is. However, the added cost and design and is really essential, such as elevated foundation and or special drainage features should be considered important aspects of the expense of the building and building a house. It is usually very costly to correct site drainage problems and the foundation moisture issue after the fact. And I've seen this especially up in Minnesota where and have the right drainage and stuff, and then it would get into the basement. And I've seen walls that were bowed out, and so I actually, you have to do something to either do a dead man anchor and pull that wall back, or at least stabilize it with some sort of barrier there. So therefore, the inspector must be very careful as to what recommended recommendations she or he makes about the site with poor drainage. So I always recommend that the water control that moisture and control the water because moisture problems are often found in the basement. And in Florida here, I've done 6 basements, believe it or not, since I moved from Minnesota. And so it's it's a different climate, but the dry conditions can be just as bad because of the seepage of water. So even in dry site conditions, foundations are continually exposed to vapor, that moisture vapor from the ground. When basements are used on site with high groundwater or in areas where fluctuating ground moisture levels due to rainfall and water table changes, there are frequently exposed to bulk water. So therefore, foundations must address potential water leakage through those cracks and the joints and capillary capillary movement of the water through the foundation materials and condensation of the moist air on cool foundation surfaces. The degree of protection requires for given site, for any given site, is determined by that is uh, how am I going to explain? The degree of protection required for any given site and selected foundation type is determined mainly by the inspector to ensure that it meets or exceeds the minimal building code requirements. The building standards and recommendations in this section aim to teach enhanced moisture resistant techniques. So just remember that controlling the water or the water is going to control you. Keep that in thought when you're doing your home inspections. Foundations that create below ground spaces on wet sites due to special attention. You have to give that special attention when you notice these wet areas. During an inspection attempts to remedy the moisture problem through waterproofing may be observed, though such efforts could have a shorter lifespan than the building itself. So moisture protections of foundations by the owner or the builder should err on conservative side when there is reasonable doubt about the moisture conditions on that site. The moisture resistant practices present in this course serve as a resource for these inspectors and can be considered during the construction of the building. There are cost-effective um, ways to correct the moisture problem when for post construction. I'm doing a house right now that I'm doing a phase inspection report, and I've had to address this primarily situation because of how the ground is actually sitting, and they need to take a swell and actually move that water. So this particularly important to backfill certain areas is crucial when it comes to controlling and preventing the settlement. And on flat sites, there may require molding of the foundation pad and coordinating appropriate foundation elevations to promote the drainage. So on the slope sites, excavating and grading the uphill direction must provide significant drainage away from that building perimeter and against that direction of natural water flow on that site. For steep slopes on retaining walls at the toe of the slope may be necessary. So keep that in mind when you're doing these inspections. Controlling and grading and backfill operations is typical residential construction is really challenging. So knowing a real good landscaper and asking them questions is really helpful. Common practices on these sites involve placing the backfill with minimal effort in to fill a hole. Proper backfill practices and grading will ensure that the foundation remains dry, more effective than other recommendations here. So foundation drainage serves several functions, such as removing free water from the foundation perimeter, which reduces lateral load on the foundation wall. So it also lowers the groundwater level around the building footprint, especially during wet seasons. Basements should not be used where ground levels are near the basement floor level. I did an inspection on a cabin once, and I opened up the crawl space area, and it was full of water. And there was some big HVAC equipment in there, and it was actually sitting up right line with the water. So, moisture control. Current building codes require drains around a foundation enclosing inhabitable spaces such as basements unless soils are naturally well draining. So here in Florida, we got a lot of sand, so it's very well draining. A site-specific soil investigation or extensive local experience confirmation really can help with that groundwater uh, inspection. So um, you got to be consistent when doing these inspections. Where the foundation drainage system cannot be drained to daylight by gravity, a sump pump must collect the water and discharge it a suitable outfall away, a safe distance from that building. And a drain, a drainage layer underneath the entire building subfloor coupled with weeps to drainage system around the foundation perimeter may be more effective in eradicating conditions where the potential of high groundwater um, extricate in conditions. So basically what this is and the experience that I've seen in trying to get rid of that moisture is putting in one of these drain tile systems. And we used to, when I was in construction, we actually installed these too. And having that going around the perimeter, and that would fill up, and then it would go to a sump pump, and that sump pump would pump it out. And I can't tell you how many places where I've been to where it would just pump it outside the wall, and then it would just come back in. So the drainage layer underneath the entire basement subfloor, that drain tile, coupled with weeps to drain that system into that sump pump for high groundwater level near the basement floor elevation does exist. So experience has shown that diverting moisture with a drainage system before it enters living space is more effective than trying to seal moisture out of the foundation. And I did one house that had a wall that was bowed in like this, and then they dug out the drainage or the drain tile and they put that in, and you could literally see the wall go like this when they finally put it on. So that was pretty cool. So the term waterproofing and damp proofing both relate to the moisture protection, um, and but are often mis misapplied or incorrectly used by inspectors. Damp proofing does not provide the same degree of moisture protection as waterproofing. Model building code, or sorry, the building codes typically require damp proofing of foundations, the foundation walls that retain earth and enclosure and interior spaces below that grade. So damp proofing involves applying one or more coatings of impervious components to prevent water vapor passes through the walls under slight pressure. So waterproofing measures are reserved for conditions with a high water table or severe soil water conditions. Waterproofing involves applying a more impermeable membrane to that foundation wall that may include damp proofing plus a layer of 6 mil polyurethane or poly on the exterior below grade portion of that basement wall. So we really want to make sure that we're protecting the interior of your living space is basically what we want to do. Other single ply or buildup membranes may also be used. Waterproofing combines sealing materials and impervious coatings to prevent moisture passage in that vapor or liquid form under significant hydrostatic pressure. Concrete and masonry constructions will develop cracks due to shrinkage effects. These cracks widen over time, providing pathways for water intrusion. Controlling these cracks is important, even though cosmetic cracks often do not affect structural integrity. Horizontal reinforcements at the top and bottom of the foundation wall help control cracking and prevent differential settlement. Epoxy sealants can be injected into the wall and masonry foundation walls to address potential moisture problems. And if you do a lot of these houses like I did, you would actually see some of these epoxies that would actually drill a hole in there and you can actually see it kind of bubble out. And I've seen that quite a bit on a lot of houses. So inspectors often find shrinkage cracks in poured concrete foundation walls, which may allow water penetration. Utility penetrations through foundation walls should be carefully sealed on the exterior face prior to waterproofing and backfilling. High quality urethane caulks and most suitable for this application. Just know that. And wall construction should be inspected for penetrations due to voids or problem areas, and um, they need to be properly sealed all the way through. So whenever you got a hole, seal the hole. It's really important. So due to inspectors working with both new and existing construction, this discussion focuses on interior installation systems for basements. Exterior installation strategies such as using foam insulated panels on the outside of the foundation wall remain vital viable option for new construction. These panels provide a moisture resistant insulation layer exterior to the wall. Mo moderating modernizing the interior wall surface temperature and integrating with that waterproofing or damp proofing. This requires shifting the house structure outward so that the sill plate protects the upper edge of the foundation insulation during and after construction. Now, there's also another, reading this, there's also another step there why I like that polyurethane foam is because if you have frost, like we did in Minnesota, it actually kind of gives it that little bit of buffer too. So I like to see that foam But I also like to see it if it was covered with something too, because we want to make sure that the sunlight doesn't start eating that. So I like when I was doing the inspections up north, that's what I would call out because that sun will eat that foam up. So basement walls finishes face unique moisture challenges. Appropriate approaches for insulating and finishing basement spaces vary depending on whether the construction is new or existing and whether the basement is only being insulated but not finished. So existing basements have limited options for exterior foundation installations. So interior installation approaches using that foam, which offers good moisture performance, requires a fire-resistant coating such as gypsum, making them suitable for finished basements, but ineffectively for merely insulating unfinished areas. So experts in the industries have different strategies for basement finishing. A successful basement finish design must address exterior waterproofing, humidity control, and air sealing properties. So the installate the illustration shows a concrete foundation wall with exterior insulation using the foam insulation panels on the outside for moisture resistance. The above grade wood frame wall, constructed of 2x6s, overhangs the foundation wall by up to 2 inches, allowing the additional rigid insulation over the entire wall assembly. This figure also depicts a sand layer beneath the floor slab. For interior installation systems, the methods il illustrated are becoming best practice in residential construction. This strategy is included here for these dealing with moisture problems under traditional practices. It is not meant to substitute for the adequate waterproofing, drainage, the humidity control, the air leakage control, low perimeter barrier retarders or vapor retarders on the interior side of the basement finishes, like the polyurethane sheeting and the vinyl wallpaper should be avoided as the trap for they actually trap the moisture vapor moving through that foundation wall, hindering the drying process for the foundation. Unfaced fiberglass batting insulation and permeable paint finishes on the gypsum wallboard are preferred for basement finished wall assemblies. So the basement finishing systems using rigid fiberglass insulation boards have performed well. However, certified installers may be required by manufacturer. Rigid foam creates a moisture-resistant material buffer between the wall finish material and the basement foundation wall. Semi uh, permittable rigid foam insulation sheathing products like the drawing a blank here. The EPS and the XPS should be used since below grade portions of the foundation wall must dry towards the interior. Product specification should indicate a perm rating greater than 1 perm. So joints in the foam sheathing should be trapped and sealed, or trapped, should be taped and sealed. So make sure that all those seams are taped. In addition, installation is desired, and the frame wall can be built in cavity insulation installed as shown in that figure there. To prevent the humid basement air from leaking into the finished wall assembly and conditioning, the interior side should be sealed against air leakage. The ideal approach using gypsum wallboard as the air barrier, requiring sealing any panel penetration or leaks. Again, you want to seal up those leaks. Air sealing, basement ceilings, penetration should also be addressed. So, section 2.5.4 discusses the airtight drywall approach. Additionally, joints in the foam insulation should be taped and sealed. Gypsum wallboard, wood trim, and wood framing work will wick moisture from that slab, cooling materials in contact and creating higher surface humidity levels, potentially supporting mold growth. Finishes and baseboard trim should be held about a half inch from the slab surface, sealing gaps and caulk or sealant to prevent indoor air leakage into the wall assembly. A thin foam plastic sealer may be used underneath the finished wall bottom plate for adding moisture protection. During basement inspections, check the bottom of the finished wall for moisture. Something that you can check out in your next home inspection when you're looking at garage doors. Look at the sides of the garage door where they actually have the trim, and then they attached um, your garage brackets on the sides of the wall. You can look at that. They always put that wood and it touches the concrete, and you can see that it actually wicks up just a little bit. So a good measure is to cut that at least here it says a half inch, and I would probably agree with that too. But you can always see that's where it always damages because it's moisture intrusion. Slab on grade constructions include the thickening edge of monostatic slab foundation constructions, giving their similarly the concrete, the masonry, stem wall, the foundations with the independent above grade floor. We'll discuss this right now. Moisture resistant installers are summarized in the diagram. They are relatively simple in comparison to required for basement construction. So, however, many of the same practices apply. Slabs below the outside ground level as the partial or full basement construction should be built in accordance with the basement foundation recommendations. A good understanding of the best practices for moisture resistant construction will greatly improve the inspector's ability to search for and diagnose these moisture problems. So, a vapor barrier, the 6 mil poly or equal, or approved vapor barrier or retarder is generally required below any slab intended as a floor for habited space. The joint should be lapped not less than 6 inches. It should be placed in direct contact with the underside um, of that concrete slab. So the vapor barrier will prevent moisture vapor from adding to the building's interior moisture load and also serves as a break for the capillary movement of moisture. A vapor barrier is a vapor retarder of the certain class. Class 1 vapor retarder. A capillary break layer, generally like it's about 4 inches of clean graded sand, gravel, crushed stone, or crushed blast furnace slag. Further prevents bulk slag or bulk soil moisture from wicking up the bottom of that slab. Building codes typically require a capillary layer below the slab and should be provided under that vapor barrier so that water cannot be trapped in the gravel layer between the vapor barrier and the slab. The vapor barrier will help to cure the concrete properly if it is properly damp cured and the top surfaces of prevention exposure to excessive drying conditions. And if excessive water in the concrete mix is avoided, um, yeah. I do like I said, I do a lot of these phase inspections, and that's one thing that I really check is that make sure that that poly doesn't have any holes in it. Make sure that it is taped up properly, especially around all those pipes that come through the basement wall. So concrete, there's two types of concrete: concrete that's cracked and concrete that's gonna crack. Okay. Uh, And so concrete will crack as a normal outcome of the curing process. Cracking can be worsened if uneven barrier conditions occur, such as uncompacted fill, right? And that exists underneath the slab. The use of welded wire fabric reinforcements provides a means of controlling the severity of that cracking, while fiber reinforcement concrete may also provide adequate crack control. The in, induction of those fibers may tend to decrease the workability of the wet concrete, if that makes sense. Um, I actually worked with a concrete worker for a while, so I actually got this pretty good. Um, but you need to work it. And to allow moisture to be more readily penetrate that concrete slab, you gotta, how do I put this? Workability will tend to allow that moisture to be more readily penetrate that concrete slab, weakening that concrete and leading to differential drying issues and cracking. Excessive cracking can allow additional moisture as well as radon gas penetration more easily through the slab, not to mention, those ants that climb up through those cracks. So, concrete control joints may also be used to control random cracking by creating planned lines of weakness in the slab shrinkage and curing. Cracks generally occur in the continuous length of concretes greater than 12 feet. So, uh, I think everybody kind of understands this that whenever, let's say I pour a piece of concrete and it's curing, then they take the saw and they actually make these control joints so that if it does crack, it typically cracks where the it most um, most vulnerable area. So that's where those control joints are so important. As the basement foundations and footings in local building codes may not require horizontal reinforcement of these thickening edge footings of the monolithic slab on grade. The the same applies to stem wall and independent slab construction. However, the information in this course will describe a minimum of continuous number 5 rebar located horizontally in the top and bottom of the thickening edge of the monolithic slab or stem wall. This allows the thickening slab edge to act as a moderately reinforcing grade beam to reduce cracking from differential settlement. Concrete and masonry stem walls may be reinforced with horizontal reinforcement bars in the manner simply to that recommendation for basement walls for difficult soil types or soil type conditions, such as expansive or weakened soils, such as concrete slab foundations may require for advisable, such as like mat foundations or post tension slabs. So this might be a little bit over your head, but that's all right. Just know that concrete needs to cure at a certain rate, and controlling the moisture with a retarder is helps that control. So building codes allow foundation installation to be placed in various locations at perimeter of the slab on grade foundation. Ideally, the best location for installation in slab on grade foundation is on the vertical outside the face of the foundation. In this location, thermal bridging or bridges are minimized, energy efficient is maximized, and the slab surface temperature is moderate to prevent the risk of um, condensation during those cold weathers. If slab on grade installate insulation is placed in a different location, such as like on that face of the perimeter wall, then care should be taken to create a continuous thermal break between that indoor portion of the slab and that outdoor portion. So now, like basement wall finishes, finishes on concrete floor slabs on grade are exposed to unique environment due to direct contact or direct ground contact. From a moisture perspective, tile, uh, terrazino, stain, decorative concrete, and other moisture finishes are ideal for slab on grade construction. These materials are resistant to flooding and other sources of moisture damage and are typically in southern and hot and humid climates. So, more like in my area where I'm at now in Florida. If a slab shows signs of pre-existing moisture problems, such as like dampness or condensation, salt deposits, effervescence or whatever, or standing water, uh, these should be addressed before moving ahead with the floor finishing. So once any pre-existing moisture issues with the slab are addressed, the floor finish assembly that can accommodate a small amount of upward moisture flow can be installed. One viable approach involves the use of rigid, semi-permeable insulating sheathing, such as like stranded polyurethane on top of the slab with a 12 to 16-inch on furring strips above that foam, followed by the layer of tongue and groove plywood for the subfloor. The finished flooring above the plywood should be breathable finish. So you have a house has to breathe, and same thing with wood, it needs to breathe. In other words, it will start wicking. With impermeable materials such as like vinyl flooring should be avoided. With this type of assembly installed, a relatively dry slab without sub layer or sub-slab layer of poly can be finished and designed to adequate or accommodate a limited amount of moisture that kind of dries upward. Hopefully that makes sense. The primary cause of moisture problems in crawl space are really poor site drainage and the lack of the ground vapor barrier and the ventilation during those humid summer conditions. Crawl space moisture damage and mold formation can be caused by many of the issues that are addressed for moisture resistant crawl space foundations. So ideally, crawl spaces construction should result in interior ground surface at or above the exterior finish grade. Extra attention is needed for foundation drainage with crawl space below the exterior grade. Venting the crawl space in humid conditions can cause condensation on cool surfaces, including ductwork and floor framing, potentially leading to water accumulation, wet installation, material uh, degradation, and mold. So, ground cover laid on the crawl space floor can become damaged over time, reducing its effectiveness and making drainage difficult if wetting from plumbing leaks. As enhancement, a mud slab, the 2-inch thick concrete, may be placed on the ground level and sloped to drain to the sump pit for wet sites. If the crawl space elevation is below the exterior uh, finish grade, foundation drainage and damp proofing, such as like the bituminous coatings, should be provided as required for the basements. Crawl spaces should use these measurements along with exterior drainage systems. There are two choices for crawl space ventilation. Conventional practice, which require a minimum net area opening based on the underfloor space area, or the non-vented design strategy. Traditionally, vented calls for a minimum net area of at least one square foot for every 150 square feet, or reduced to 1 to 1 500 or 1500 when using the class 1 vapor retarder. Vents should be on at least two opposite sides of the foundation near the corners and high on foundation wall. Inspectors should refer to applications building codes before recording elevations. Okay, non-vented crawl spaces are also recognized as suitable, especially in hot and humid climates where outdoor air adds moisture. This method involves several factors in the functional, exterior grading, and the size drainage, minimizing the air leakage between outdoor and crawl spaces, insulation on the perimeter walls, such as rigid foam. Use a 6 mil polyurethane ground covering, damp proofing of the foundation wall, some ventilation with conditioned air. I did do a inspection with a crawl space that was not vented, and we had some major moisture issues. So make sure that you're checking every space that you can. So we were talking about the crawl space and moisture intrusion, vented versus vented or unvented. So understanding vented and versus the unvented crawl space. Vented crawl spaces can minimize radon and moisture related decay hazards by diluting crawl space air, but do not necessarily dissolve serious problems. Disadvantages include insulation needs against the heat, the loss, the freezing, increased insulation areas and those costs, and potential moisture issues in the wood. Operational vents can reduce winter heat loss and keep out moist air in the summer. Venting is unnecessary for moisture control if open to an adjust basement and uh, incompleted with the crawl space used as heat distribution plenums. So basically, there's two theories of vented and unvented crawl space, and I'm not going to get into all, but this one builder got it approved that he didn't have to put vents in this crawl space. And so this realtor I was friends with, he said, could you come out and check out this house? Because for some reason I'm getting moisture everywhere. And so I did my moisture meter and we ran some water, ran everything, and I couldn't find where this moisture was coming from. And the only thing I could think of was maybe they needed to put some vents in that crawl space. And sure enough, he finally put some crawl space vents in, and guess what? All the moisture actually escaped and we didn't have any more moisture problems. So insulation, those areas is crucial. Those operational vents are really helpful, and unvented crawl spaces may reduce the insulation needs and it simplifies it. Minimize condition can or condensation. It minimizes that condensation hazard. So many agencies are unwilling to endorse closing vents year round due to common moisture problems, just like I said here. Soil types and groundwater level influences the moisture conditions. So crawl spaces can be designed as short basements with slurry slab floors, generally less accessible to moisture. The main distinction between unvented crawl spaces and basements is accessibility and the likelihood of noticing moisture problems. Since we noticed that moisture problem, we were able to address it, and I was able to help him, and I'm still one of his favorite inspectors. So better be. I'm related to him. Just kidding. Decay of common wood framing materials can begin when the moisture contents of untreated wood exceeds that 20%. In foundation and building applications, these conditions should be avoided by adhering the minimum ground clearance and detailing the requirements. The ground clearance outlined in this section are considerable minimums and have worked reasonably well in typical climates. In climates with frequent rainfalls for the site with continuous moist ground conditions, greater clearance are recommended. In addition, capillary breaks are important, particularly when clearances are at minimums. Capillary breaks help to protect wood from wicking up. Moisture wood will always wick around that foundation from that ground. Capillary breaks may be in that form of materials such as metal flashing, tarred felt paper, sealed sealers, foam strippings, and polyurethane. When wood has direct ground contact, it needs that clearance. Or if the clearance are less than those required, then pressure treated wood should be used. And I don't understand why people don't use it. So, moisture around the foundation from the wall, capillary breaks may be in the form of materials such as wood I just described. So, when wood has that direct contact, that pressure treated wood um, or that moisture resistant layer should be used. So, try to use some of that, or try to um, visualize some of that material. So if it is pressure treated wood, you should be able to see that it is just by if it's green or red color. Most building codes require a 6-inch minimum clearance between the untreated wood and the exterior grade. And some codes allow the 2-inch reduction in this clearance if brick veneer separates internal wood materials from that exterior grade. A minimum of 8 inches clearance between untreated wood and the exterior ground level is recommended by many experienced building inspectors. In other conditions shown in this figure, ground clearance recommendations vary. So, for example, like you got your floor beams in the crawl space are required like a 12-inch minimum, so 1 foot clearance to that interior grade, as much for a reason of access and for that moisture protection. So we really want to make sure that we can see when you're going underneath, or at least try to get some good pictures in there when you're doing that. It's really important, not just, protect yourself too, because you want to make sure that you're seeing and describing what you see, uh, especially for moisture intrusion. Like I said, one of the most call out things for insurance companies. So often there are situations where wood cannot be adequately separated from the ground moisture or protected from exterior moisture sources. In these situations, either naturally decayed resistant wood or preserved treated wood must be used. In some cases, wood alternatives may be considered, such as the plastic porch post with metal pipe inserts, the plastic decking, the concrete post or piers, or the plastic lumber composites. Those are pretty cool. Those type of wood can actually really help with preserving um, the wood above it. The focus of the section is to identify the proper specifications and the use of pressure treated wood to ensure the moisture, the decay resistance, um, and durable performance. The recommendations in the section are based on those standards and recommendations in the Southern Pine Council and American Wood Preservers Association, also known as the AWPA, which I totally forgot about. Uh, in recent years, changes have occurred in the availability of certain wood preservatives, treatment chemicals for the use in residential products. Therefore, it is important to understand how these changes affect treatment requirements for various types of wood and applications, in particularly the use of the CCA, the chromated copper arsenate. I believe that's what it is, has been discontinued as a wood treatment, except in certain commercial and agricultural applications for like pile foundation, the fence post, things like that. However, there are exceptions. For example, the CCA treated lumber and the what is it? The CCA treated lumber and the plywood are still available for use in permanent wood foundations. In residential as well as commercial, the agricultural applications for most residential applications, however, newer forms of treatment are the only choices. So, fun stuff in it. It is important to realize that many of the new lumber preservative treatments may increase the corrosion rate of galvanized fasteners by a factor of 2 or 3 under standardized test conditions. Therefore, in cases of exposure to moisture at decks, porches, and balconies, it is recommended that stainless steel fasteners and connector materials be considered. At a minimum, hot dipped galvanized or G120 galvanized coating should be specified for the steel fasteners and cold forming steel connectors. A G120 coating provides at least twice that galvan coating commonly used for framing connectors in residential construction. Connectors within the building envelope and are in contact with newer lumber. Uh, preserv Preservative treatments are generally accepted, such as the half-inch diameter sill anchoring bolts. Now, just to tell you that one time I was building something and I did not pull old codes or nothing, but I had all these joist hangers that I got from a site once. And so I decided to use them on this wood. Within a year, they started rusting. And so that's when I found out that the solvents that they use in that pressurized lumber actually ate that coating. So it is very important that you use the right joist hanger. And that actually happened to me personally. So other types of foundation wall construction methods and materials are less frequently used in the United States, including the permanent wood foundations, the other words known as PWFs, the insulated concrete forms, the ISF or ICFs. I don't know how to spell, I guess. Precast concrete foundation and elevated foundations in flood-prone areas. So these systems are not specifically addressed in this course, except to mention that they are important foundation moisture management practices that may be required. The inspector should carefully consider manufacturer and industry recommended practices. In addition to those relevant building codes, the minimum building codes, just FYI, when inspecting these types. With proper consideration and installation, these systems provide dry and serviceable foundation systems. So I've done a few peer inspections here in Florida. I did a few up in Duluth area, and it was it was quite the head scratcher for me. And now that I've done a few of them, now I actually know a little bit more about it. So, anyways, we won't going sidetracked. ADD. In the northern U.S., moisture barrier vapor problems are driven primarily by indoor relative humidity, which is the RH, combined with the low outdoor temperatures during the winter. In the southern U.S., especially the southeast, the problem is largely driven by high outdoor humidity and low indoor temperatures during the summer months. So I went from one extreme to the next. Mixed climates are exposed to both conditions and can experience both types of problems. Therefore, many of the best practice recommendations in this section vary according to the climate. The same is true of the underlying building code requirements. Unfortunately, there is no uh, definite and there's no widely accepted um, climate mat that addresses all the climates in factor, and that contributes to the moisture vapor problems. There are perhaps too many variables in climate and construction practices to treat the issue without significant use of experience and judgment. So various climate maps and criteria have been applied in building codes in the past, and more recent building codes continue to demonstrate a lack of overall agreement among the experts, just like your vented and non-vented. It is for these reasons that acceptable practices for moisture vapor control often vary based on local experience and difference of opinion. So, like I've always said, you have to understand where water's coming from and where it's going. If you don't control that water will control you. So make sure you kind of keep that in the back of your head at all times when you're doing inspections. Moisture problems related to moisture vapor can be confusing because they're caused by several types of moisture. Sorry, my phone's going nuts. Of course it is, because it's just the way it is. Um, sorry about that. Uh, so several types of moisture sources can be result from different types of dynamics in the house. Also, seemingly unrelated decisions that are made for one building system, such as how to lay out the HVAC system, are not at all independent and will affect the migration of the water vapor in the house. The high indoor humidity, uh, like greater than like 40% in the winter and greater than 60% in the summer, that's the general range, is primarily caused from many vapor-related moisture problems in the home. From a moisture perspective, very low indoor relative humidity levels are helpful to control condensation and related problems. But other important factors that actually require such minimum levels of indoor um, RH to be maintained must also be considered. So these include a minimum humidity level to keep occupants comfortable, approximately 25%, um, is the minimal humidity to keep wood finishes and furniture from drying out, and for homeowners with special needs for higher indoor humidity. So the relatively humidity levels really can affect how you live too. And there's been a lot of discussion on that. And one of these days I'll probably have to go into detail about that. But one time I did a um, home inspection. It was about 20 degrees below zero. And I opened up the door and all this like vapor came from the outside, from the inside to the outside. And it was like, whew. And when I was in the house, like even around the windows and everything was all like water driplets everywhere. So that relative humidity levels are a big concern. The whole house and spot ventilations to dry outdoor air could be installed in ventilation controls that automates that uh, could exhaust could be added. So like one of those ERGs or something like or ERVs could be related or HRV could be related. Anyways, I'm getting ahead of myself. The high RH levels might be concerned based on the local experience and the climate. High expected occupancy load, usually occupant habits, or especially tight construction, providing for increased ventilation means selective higher capacity fans for whole house or local ventilation devices, like I was just talking about. One option is continuous fan operation at a low level with the local switches that can boost the fan speed temporarily. In humid regions, the additional of damp outdoor air without any treatment of the new moisture load will actually add moisture to the house instead of helping to control indoor relatively relative heat or relative humidity. Heating, cooling, and ventilation systems in such climates should be operated to accommodate additional moisture loads resulting from that ventilation. So, inspectors should really consider documenting the existence of the supplemental dehumidification that is observed during an inspection. The presence of a dehumidifier units may indicate that the homeowner has some concerns for too much humidity or needs some extra humidity control. So supplemental dehumidification systems address indoor relative humidity by managing both the built-in moisture in the new houses, like the water that dissipates from the new concrete basement, and ongoing moisture loads in existing homes. Controlling ongoing moisture loads is essential, important in areas with humid shoulder season when the AC system will not run operation for cooling, but indoor humidity must still be removed. So no matter what, you have to control the moisture, you have to control the water. And I've been to many houses where they had like three humidifiers in their house, and I'm like, ooh, there is definitely a problem going on in here. When I was doing the full home inspection, I did realize that their coil on their air conditioning unit was actually really clogged. So pretty simple fix, but some people just can't see past what they know. So air leakage can transport significant water vapor, impacting moisture issues in the building. To minimize the air leakage, building envelope should be sealed with an appropriate air barrier system. Considering climate conditions, home inspectors must understand air leakage dynamics. Factor driving air leakage include wind, stack effect, and forced air or HVAC systems. Um, Air barriers help mitigate these issues. However, sealing practices might reduce combustion air supply for fossil fuel equipment, causing backdrafting of combustion products. So, sealing combustion equipment and mechanical ventilations are recommended to address safety concerns and indoor air quality. Vapor barrier materials must manage vapor movement and water shedding based on the location within the wall. Building codes mandate air sealing around framing joints, utility penetration, drop ceilings, um, and other areas preventing air leakage. So, suitable sealing materials include air barrier materials, caulking, sealants, tapes, gaskets, and the list goes on. So, inspectors should prioritize major air leakage points, such as mechanical chassis, attic access hatches, plumbing stacks, penetration, exposed wall cavities. Cathedral roofs require careful sealing to prevent condensation and moisture problems from humid indoor air entering into the cool roof cavities. Reducing air leakage is essential when you're and air barrier systems aim to block those leaks while addressing the rainwater protection and vapor return. So, effective air barrier materials such as the gypsum wallboard, the spray polyurethane, foam, uh, the wall structure panels, the foam boards, the building wraps, seams in these materials must be sealed. So, this ensures a lot lower permeability so that we got to control that moisture. And how do we do it is through understanding to seal everything up. In cold and very cool climates, uh, the primary concern is preventing interior warm and humid air from flowing outward into the building exterior envelope assembly, especially during those winter months. The airflow can carry a large amount of moisture and cause condensation in the wall, kind of like if you had a cold glass of water, yeah, or a hot glass of water outside, whatever. Sorry. So the airflow can carry a large amount of moisture and cause condensation in the wall. Therefore, the use of interior air barrier system in cold and very cold climates is preferred and may be combined with a warm in weather vapor retardant. A veritable approach in such regions is the ADA method used in conjunction with an interior vapor retardant layer such as craft face bats or vapor barrier paints on drywall. Use of the APA method should be applied more cautiously as such loca- loca- localities and building sciences are concerned that the layer is almost too airtight and vapor impermeable and shouldn't be allowed drying to the interior of the building at any time of the year. So there is some clashing there. In damp and humid climates, the primary concern is preventing exterior warm and humid air from leaking inward from the exterior surfaces into the building envelope assemblies. That will be cool from the air conditioning. So in damp and humid climates, an air barrier system is preferred on the outside of the wall. Many exterior sheathing products and wraps can provide this function and can also serve the water barrier function underneath siding materials, the ASA and the AWA methods. Okay, in climates with mixed conditions, the most suitable air barrier system can be selected based on the construction characteristics and then combined with these systems. For example, if a building wrap is used as part of a drainage cavity, weather resistant envelope, then the air type wrap approach, the AWA method, can be used with a little extra detailing of the building wrap, such as taping the overlap seams, sealing them simultaneously, extra attention to seal interior dry joints, penetrations that may be airtight. Uh, so that's the drywall approach for a reasonable strategy. Just seal, caulking. So in hot, humid regions, walls must dry toward the interior. Homeowners should avoid non-breathable finishes like vinyl wallpaper or vapor barrier paint. Vapor retardant materials on the inside can cause condensation issues. Use semi-permeability, semi-permeable. I can't even say that word right now. Sorry, guys. Use the semi-permeable materials such as the unfaced fiberglass bats with permeable interior paint. Incorrect installation of vapor returns often cause moisture problems. Vapor diffusion, high indoor humidity, and air leakage contribute significantly to these issues. Properly installed vapor retardant prevent humidity within building assemblies. In hot, humid climates, exterior wall systems should dry inward by placing the vapor retardant outside and keeping the interior materials vaporized uh, permittable. Tell you, I am having a hard time right now. Sorry about that. In cold climates, walls should dry outward by using vapor retardants inside and ensuring exterior materials are vapor permeable. Common sheathing methods with low perm ratings may impede drying, which is under investigation by the building sciences. So these things are always going to be changing. So if you can get that air movement through certain materials, it's going to change depending on where you're at. And sometimes it's all about how the building envelopes needs to be dried from the inside out or from the outside in. So this section here describes moisture control and moisture related problems concerning the design, installation, and operations of mechanical systems, such as heating and cooling equipment, ductwork, ventilation, common moisture issues that can arise from residential mechanical systems are covered. Now, the commonplace rule of thumb sizing methods, such as like 1 ton of cooling per, I don't know, 400 to 800 square feet of conditioned floor area, should not be used in place of building specific load calculation method. Okay, although still potentially a problem, oversizing an AAC systems from using the rule of thumb method causes increased short cycling of the cooling system. Short cycling reduces energy efficiency and can decrease the moisture vapor. Removal of capillarity of conventional AC equipment by as much as one half of the rated uh, ladle heat removal capacity. So basically, what happens here is if you have too big of a system, it cools way too quick. Then in the process, everything is cool in the house, but that moisture ends up collecting in those ducts and stuff. So you end up with more moisture than, well, not more moisture, but not a way of getting rid of it. So first, the indoor relativity humidity levels are increased as the AC reduces the air temperature but removes moisture to a much lesser extent. So when I moved into this house here, we actually had a too big of an air conditioning for such a smaller area. And when I got it removed, we actually had tons of mold inside that air conditioning unit. So it's very important to understand that too big uh, doesn't mean less moisture. So, second, due to the increased indoor humidity and discomfort, occupants may lower the thermostat set point temperature to compensate. As a result of cooler indoor temperatures, approximately less than 75 degrees Fahrenheit and higher indoor RH levels, condensation is more likely to occur on the windows and doors, on the inside of the wall cavities, on the concrete floor surfaces, and on floor seating and joists above the crawl space. For that reason, this guide emphasizes the importance of using the ACCA Manual J or other similar cooling load calculation produced to size HVAC equipment. It's very, very important. And I can't tell you how bad, like, I our concrete would sweat, and yet it was cool in the house, but we had this like odor. And now that we actually got it sized properly, I don't have that sweating problem like they did. Not me, but the concrete. Even with the proper sizing of heat pumps for heating and cooling loads, there are significant times of the season where systems will operate under part load conditions rather than design load conditions. Thus, accurate sizing of equipment only lessens the short cycling problem. To provide improved moisture removal and energy efficiency, two-speed compressor heat pumps and variable speed blowers should be considered. And that's what we have now. These systems operate on a lower capacity much of the time, providing enhanced moisture removal and more efficient operation. Such systems offer the greatest benefits in your area in areas with long cooling seasons like I have here, and are also a good match for two-zone systems because they can effectively handle single or dual zone operations. Supplemental dehumidification controlling indoor humidity in damp, humid regions or enhanced moisture removal from the HVAC equipment is recommended in damp, humid region as a means to control indoor moisture levels. Again, if you're not controlling that moisture will control you. Or so in other areas where less prolonged periods of high humidity, these systems should still be considered based on the benefits such as better control of indoor moisture, enhanced comfort, and integration with fresh air ventilation. For new basement foundations, supplemental dehumidification will also help remove moisture from the foundation as it dries, which can help prevent moisture problems in finished basements. Supplemental actually means some type of dehumidification equipment besides the house AC system. These systems range in cost, quality, and function. A few dehumidification systems options are discussed as follows, okay? The portable dehumidifiers. These are the simplest of supplemental dehumidifiers and generally provide adequate dehumidification for a small volume of air, one room or just a small basement. They are relatively inexpensive and can include humidity sensors and controls that regulate their operation. These units may require frequent attention to assure that they are disposing of condensate properly, unless they are plumbed to a drain. I've seen that happen. They also give off waste heat into the area where they're located. When a portable dehumidifier is observed during a home inspection, its existence and operation should be documented. So make sure you document all that stuff. It may be an indication of a moisture related concern or problem being addressed by those owners or the occupants. So stationary dehumidifiers, these systems are available in a range of sizes for small and large jobs. These are designed including like the one standalone single zone system, or they may be incorporated into the forced air duct system. These system, which also gives off waste heat, have the advantage of a plumbed condensate drain line that does not require frequent attention. So there are some benefits of that one. Dehumidifiers, ventilators, these systems are also standalone systems used to dehumidify the air, but they also include capillaries for fresh air ventilation and air filtering. These ability to introduce and dehumidify outdoor air with a single unit mitigates the moisture and ventilation air can bring into a house, which is the major concern in hot, humid climates. Furthermore, since dehumidifying ventilators are an independent piece of the equipment, they can be used to control indoor humidity during shoulder seasons when the central AC system does not run. Another big issue in hot, humid climates. So, sealed combustion chambers should not create moisture problems. The use of sealed combustion or of the HVAC equipment is ideal because it helps to alleviate that potential backdrafting, and it also helps to control pressure differences across the building envelope. Controlling the air pressure difference across the building envelope helps to minimize air leakage and the migration of moisture into the building assembly. So sealing the combustion equipment such as a sealant combustion natural gas furnace draws all the air from the combustion directly from outdoors via deducted dedicated duct, and combustions that air and fuel in a sealed combustion chamber. So it, everybody's seen these, especially where you guys are from. So sealing those ducts reduces that air leakage and moisture, just to make it simple. Building codes require that joints in duct system be made substantially airtight by means of tape, mastics, gaskets, and other approved method. This guide recommends sealing duct systems such as air leakage to the outside of the building envelope is 5.0 CFM, um, or 25 to 100 square feet of floor area, I believe. So, anyways, the the measurement CFM 25-inch denotes the air leakage from the duct system measured at the duct pressure of 25 pascals. So, actually testing of the duct system with a duct blaster tester can be conducted by a home energy raters or utilities. Suitable sealing materials include like the UL 181 rating, foil tape, and mastic, I believe. And you'll see that foil tape quite a bit, especially when you're doing a lot of homes, and I totally recommend it. Sealing air leakage from ducts has two important advantages. First, it improves HVAC system energy efficiency, and second, it reduces pressure imbalances that can cause air leakage through the building envelope. This air leakage can transfer a large amount of moisture into the building assembly and cause condensation and related problems. For example, a house with leaky supply ducts in the attic can become depressurized, resulting in warm, damp outdoor air being drawn into the building envelope during the cooling season. A particularly troublesome problem in hot climates, or hot, humid climates, I should say. Airflow can transfer through the building assemblies into the amounts 10 to 100 times more than that which would typically occur by a vapor diffusion. So, conversely, building pressurization from a leaky return duct can cause humid indoor air to exfiltrate exfiltrate into the thermal envelope where it may condensate on cold surfaces during winter condition. Inadequate air return cause moisture problems as well. Most central return systems do not provide adequate pathways when interior doors are closed because door undercuts do not provide enough flow area for the returned air. As a result, some interior spaces become pressurized and others become depressurized. Both of these conditions can drive air leakage and moisture transfer. An ideal return air system provides unrestricted pathways for the return air to travel, excuse me, travel to the return grills. To achieve this type of return system, the inspector should see multiple returns with the ducts formed from actual duct material and not building cavities, such as like the joint bays, the most expensive alternative, but also the most effective, or jumper ducts and transfer grills to provide return air pathways from rooms that can be isolated when interior doors are closed, which is moderately effective and moderately expensive, but may carry privacy objections. So, what's the dark stain at a carpeting perimeter? Hmm. In addition to elevating pressure imbalances and limiting air leakage through the building envelope, these practices can also provide comfort in eliminating soiling problems that leave darkened stains on perimeter of carpets. Whole house mechanical ventilation is good. The whole house mechanical ventilation systems are recommended to provide fresh air and keep a range of indoor air contaminants. Systems should be designed based on the ASHRAE standard, the 62.2 to be precise. Ventilation and acceptable indoor air quality in low rise residential buildings. The benefits of having a whole house ventilation fan installed can be conveyed to the homeowner client. A wide variety of potential ventilation systems may be used, from high-end equipment that introduces um, the filters and the dehumidifier outdoor air based on flexible controls, all the way to the basic low-cost systems that simply run a duct from the outdoors into the return air plenum. Beyond sizing systems appropriately, a number of other designs issues should be considered. For cold climates, consider ventilation systems that are balanced, air out, air in. So pretty simple, or exhaust based. Um, by keeping the indoor environment as a neutral or slightly negative pressure relative to the outdoors, moist indoor air is not forced outward into cold building assemblies where it can condensate. However, it is critical that the exhaust system do not create that negative pressure levels that can greatly affect the drafting of combustible appliances like your water heaters and um, your furnaces and stuff. So ventilation systems in cold climates may also include systems with heat recovery, the HRV, like I talked about, just mentioned a little bit. For example, a heat recovery ventilator exchanges heat from the incoming cold air with the exhausting conditioned air for reasonable energy efficient ventilation. The the incoming dry air also serves to control indoor humidity levels because an HRV matches the incoming and the outgoing airflows. This type of system provides balanced ventilations. For damp, humid conditions, consider ventilation system pressurize the indoor environment that helps prevent the infiltration of the hot, humid air into building assemblies where it can condense. Another important feature of the whole house ventilation system for hot and humid systems is call it anyways, the clients uh, has to understand like the feature of the whole house ventilation system for the hot and humid climates is accounting for the added moisture load introduced into the house. And that in such areas, the additional latent moisture load should be addressed either through the direct dehumidification in the ventilation system or through the use of supplemental dehumidification. So this has this has to be tested. So finally, testing and balancing the mechanical systems of the ventilation system is also recommended, especially when contractors are installing whole house ventilation. Simply devices such as flow gauges can help ensure that that system operates close to their design flow rates. In many cases, as build installations achieve only half of the intended airflow and controls and timers may not be installed correctly. So, building diagnosis firms and home energy raters can often provide this type of service. Check that all the exhaust ducts terminate outside. Just FYI, I did a house for a person. I did a lot of these HRVs in Minnesota, but when I caught here, I didn't see too many of them, but I did run across an ERV and she said that she talked to six other people that didn't know what the heck it was. And so I actually explained it to her and it was pretty cool. So they are found here, just not as much as they are up north. It is not uncommon for a home inspector to find clothes dryers vented to an indoor or enclosed building space, such as like your crawl space. Uh, it is also common to find bathroom exhaust fans vented into the attic space. I find that a lot for merely uh, directed towards the attic vent. These practices are prone to create moisture vapor problems and should be avoided. Home inspectors should recommend that all exhaust vents be directly vented outside and through the roof ventilation fixtures or grills. Exhaust ventilation ducts should also be attached and supported like any other ductwork. Finally, exhaust fans are rated 50 CFM based on a limited amount of back pressure due to type and length of ductwork and bends in the ductwork. Therefore, duct lengths longer than 25 feet, less than 5 feet for each 90-degree bend should be avoided unless appropriate designed if long duct runs are unavoidable. Larger capacity fan units could be used. When you see efflorescence, that is a good sign of moisture intrusion and it should be documented. But right here is how the building envelope actually uh, if you're wicking up for moisture. And I'm just going to play this video here, and you can actually see how moisture actually wicks up. And that's how wood can actually deteriorate and get soiled and so on and so forth. So, water damage and prevention, make sure that you're checking the outside, you're looking at the roofs, you're looking at how the downspouts are, looking at the building envelope around the sides, everywhere you possibly can, because this is how we can prevent moisture. And you want to give the homeowner the most information you possibly can without scaring them at the same time. So look for the kitchen, look for underneath the sinks, look for all the places where it could be preventable. When you're looking in the bathrooms, especially like around the toilets, underneath, if you can get into behind the tub, I always fill up that tub right to the overfill and put as much pressure as I possibly can on those pipes to see where the moisture can be. So that's always really important. Kick out flashing, super important. Where the wall meets a lot of the fascia and stuff, check that area out. These areas can really um, be prone for moisture intrusion. When you're looking at how things are set, and keep an eye out for drippage and things like that throughout the entire house, especially when you go around the exterior of the house. Um, the helpful links, you can always check a lot of the stuff out from InterNACHI. InterNACHI will have a ton of information there. And I think we're going to kind of end with that. I hope this really helped. I really hope that you stay tuned for the more videos from InterNACHI. We are just really thankful for this time with you, and it is 9 o'clock, and we just want to wrap it up right there. And again, I hope you guys enjoyed this. I know I did. And yeah, that's it.